So we've got a point on our surface here, and we want to follow that point. So we're told that the radius of our disk is 0.5 meters. The angle that we're starting at is 60 degrees. And our initial, when we start everything, our initial angular velocity is going to be 2 radians per second squared. And we want to know after 5 seconds, what's the new angular velocity, what the new linear velocity is, the new tangential velocity, and the new position. And last week we showed that if I have linear items or rotational items, we can build our toolbox that looks like this. V final is equal to V initial plus acceleration times time. And we had omega final is equal to omega initial plus my angular acceleration times time. We have V final squared is equal to V initial squared plus 2 times my acceleration times my change in position. Over here, we're going to have an equation that looks like this. Times my change in angle. My change in position is equal to my initial velocity times time plus 1/2 my acceleration times time squared. Over here, I have a change in angle is equal to my initial velocity times time plus 1/2 my acceleration times time squared. Hang on just a second. I want to make sure I have everything associated with my, oops. There we go. Oh, come on. Okay, I want to make sure I have everything associated with my problem. Okay, that, I knew something wasn't right. This is my angular acceleration. I had it in the right units, and this morning I just wrote it in the wrong spot. And we're traveling at a constant angular acceleration. And we are going to travel with an initial angular velocity. And I'm going to give us an initial angular velocity. I'm going to go ahead and do that as 2 radians per second. So we're going to travel at a constant angular acceleration. I have an initial angular velocity. We have our toolkit, but we also want linear velocity and tangential velocity. My linear velocity is going to equal R omega, and my tangential acceleration is going to be equal to R alpha. And this allows us to translate make sure I'm writing everything down correctly. This allows us to translate between our linear frameworks and our rotational frameworks. Okay, so there is nothing that says we have to do these in any specific order. So it's pretty easy to do the new position because I have everything. So let's do that. Let's do my position first. I'm going to have my initial and my time plus my 1/2 my acceleration times time squared. We're given our initial. We're given our constant acceleration. We're given time. So I can go ahead and calculate all this. So my change in angle is going to equal 2 times 5, and this is going to be, I've got radians per second times seconds. So I'm going to end up in radians, and I've got 1/2 2 radians per second squared times my 5 seconds squared. So I'm also going to end up in radians. So everything is going to be in radians. And I'm not multiplying very well in my head today. This value is going to be 25 radians, and that value is 10 radians. So my total change in angle is going to be 35 radians. But we have no idea what that's going to look like. That's my change in angle, but we have no idea what that's going to look like in my position. So what we're going to do is we're going to look at where we started. So we have a change in angle of 35 radians, but I need that in degrees. So 2 pi radians is equal to 360 degrees. So if I have 35 radians and I want to convert it to degrees, I'm going to get my 36 degrees, or 360 degrees divided by 2 pi. It's going to give me my degrees. I'm going to have 5.57 times 360. And that says 2005 degrees. But the reason I left it out like this is that tells me we go 5.7 or 5.7 times around the circle. We're going 5.7 times around the circle. So if we're starting at 60 degrees and we go around my circle 5.75, the new angle that I'm going to end up at is I need to know where my 0.57 is. And that's 0.57 of my circle. So I don't necessarily have to go to do that 251. Let's look at my 0.57 times my 360. That's another 205 degrees. So my final position, this is 270 degrees. My final position is going to equal my 205 degrees plus my 60 degrees, which is going to give me my 265 degrees, which means that my final position of my point is going to ultimately be here at 265 degrees. So if I'm drawing my picture as to where that is, that's where it is. Now the change in angle that the point went through is going to be 205 or 2005 plus 60 degrees. That's the entire change in angle. And if I wanted to know the linear distance that that point traveled, that is going to be my linear distance, S, is equal to R theta. And I want to stay, and my R was 0.5 meters, and my theta ended up to be 35 radians. So that is going to end up being 35 times 0.5, 17.5 meters. So that's the linear distance that that point traveled. My final position is going to be based on where I am on the circle. So there's a couple ways you can approach it, but that's one way to look at it. So let's find the new angular velocity. So we want angular velocity final is equal to my angular velocity initial plus my alpha times time. My alpha was 2 radians per second squared. My time was 5 seconds. And my initial velocity was 2.0 radians per second. So I'm just going to plug in my numbers. I'm going to get 2 radians per second plus, and that one was 2. Sorry, I said it, but I didn't write it down. 2 radians per second squared times my time, which is 5 seconds. So I'm in radians per second here. I'm in radians per second there. So I've done everything correctly. So I get 2 plus 10 is going to equal 12 radians per second. That's my new angular velocity. We want to know the linear velocity at that point. That's going to be V is equal to R omega. Our R was 0.5 meters. My new angular velocity is 12 radians per second. I no longer carry the radians, so I'm going to get 6 meters per second. My new tangential acceleration, that's going to be R alpha, and that is going to be my 0.5 meters times my 2 radians per second squared, gives me 1 meter per second squared. I could also calculate my centripetal acceleration, because as we saw in the video, that's my V squared over R. We want to use that linear one. So I'm going to get my 6 meters per second, and that's going to be squared divided by my radius, which is 0.5. And this is going to give me, and I'm going to end up, and that's meters. So I end up with meters per second, meters squared, second squared divided by meters. I end up in meters per second squared, and I end up with a value of 72 meters per second squared. And if I want to compare that with G, that's roughly 7.3 times my acceleration due to gravity. So you can, oops, sorry, that way you can actually see that. So we can do a lot of things just by looking at how something is traveling around a curve. Now let's say that this was a spider because it's Halloween time. Okay, and we've done all of that calculation. And what we want to know now is at that time, at t equals 5, what is the total acceleration? Now my total acceleration, the magnitude of the total acceleration is going to equal the square root of my tangential acceleration plus my centripetal acceleration. And the angle is going to be the arc tangent of my tangential acceleration divided by the centripetal acceleration. We already found that my tangential acceleration for this one was equal to 1 meter per second squared. My centripetal acceleration was equal to 72 meters per second squared. So if I plug in those numbers, I'm going to get the magnitude I'm just making sure I wrote down my numbers correctly. This is going to be about 72 meters per second squared, which kind of makes sense because that's a low number. And note, make sure your calculator's in radians. And I'm going to get 0.014 radians. Or if I want to do degrees, you can do that in degrees. That doesn't really matter. And this would be 0.796 or approximately 0.8 degrees. Just watch your units here. And watch the units that WebAssign asked you to put in, because that's going to be one of the things that you have to worry about from WebAssign.